Greetings, everyone. All right, so for the intersection 5.1, or maybe not the very end, because we were doing some approximations using some tabular data, but at some point in section 5.1, we said that the area bounded by the curve was the limit as the number of subintervals or rectangles goes off to infinity of the sum from I equals 1 to n, f of x sub I star times delta x. Now, this is what it means to find the area bounded by a curve and the horizontal axis, the curve F, and the horizontal axis from A to B. But this is not the common notation that you're going to see in calculus going forward. And so I'm going to show you this new notation that we're going to get in place of this notation that you're currently looking at, and then talk about some aspects of it, and then you should go off and do a Desmos activity that's associated with this section to further develop your understanding of the symbols and concepts that we're learning right now. So let's switch over to a new set of symbols. I'm going to change colors for this. Okay, the area is now going to be written with this stretched out looking S that looks like this, called the integral symbol. And we're going to put A and B right here. And we're going to put our function f right here. We're going to just say f of x. And then we're going to put a dx right here. And this is what we mean by area. Now let's go back up here to this notation really quickly. Something I didn't write down here, but we wrote down when we developed this notation, was that delta x was equal to b minus a divided by n, and a and b were the endpoints of the subinterval on which we were finding this area, and n was the number of rectangles. And of course, we're letting the number of rectangles go off to infinity. So this symbol here, and I'll start calling some things. As I said a moment ago, this symbol is called the integral symbol because it has these values a and b here. This is called a definite integral. We'll start using that notation more and more. Now, a is our left-hand endpoint, but in the context of this set of symbols, we call this the lower bound. Or the lower limit of integration. This whole process is called integration. And I'm going to write both of these things down here. Lower limit of integration. B is called the upper bound or upper limit of integration. And again, B is the right-hand endpoint. Excuse me for taking my time there. And so when Leibniz, who put together this notation, was putting this notation together for the integral symbol, he used really just a stretched out S. It is just an S for summa, for adding together the areas of these rectangles. In this notation up above, we're using the Greek letter sigma as, our representation for telling our audience, whoever's reading this notation, that we're going to be adding things together. So he wanted to keep that same spirit, but he wanted to switch over to the Latin alphabet here and use, instead of the Greek alphabet, he wanted to use a stretched out S. Don't call it big S. It sounds like you're saying big ass. It is an integral, and it is a stretched out S like that, though. But call it the integral. You want to sound like you know what you're talking about. Now, notice up in this formulation at the top, we have as our input into F, we have x sub I star, but you don't see that here. This is just x. Remember, as we said back in the development of 5.1 of this notation up here, that x sub I star was any number between x sub I, the left-hand endpoint of that subinterval, and x sub I plus 1, the right-hand interval endpoint of that subinterval. And so as we let n go to infinity, as n gets larger and larger and larger, these intervals are getting smaller and smaller. And in the extreme, this is one metaphorical way of thinking about this, but in the extreme, as n goes to infinity, we don't really have a choice any longer about x sub I. X sub I is just going to be squeezed down to be the local variable x. Okay, so we don't see x sub I started in here. We just see f of x because it's just going to be our function of x. Now we do want this dx over here. The fact that we're using the same letter is important. We're going to see that most of the time here. When you go on to multivariable calculus, and you'll see something called double integrals or triple integrals. You're going to have various variables, within the different integrals that you have, and you'll have a dx and a dy and a dz possibly, or some other versions of multiple integrals. But we want those to match. Okay. Now the dx that we have here is a remnant of the delta x that we had over here. Okay. Dx in the integral notation, I like to tell my students, is like the closing parenthesis of an opening parenthesis. The opening parenthesis is like the integral symbol over here, and the closing parenthesis on this end over here is like the dx. Let me make this integral look a little more stretched out. We don't want to start a parenthesis, have an opening parenthesis without a closing parenthesis. When I was in college, if you were to write an integral symbol and did not have a dx or dy or dt or d, whatever variable the expression was in for f of x, then your notation was nonsense. The professors wouldn't accept it. They wouldn't interpret it in any way. And basically, you would receive no credit for it. So be careful. You always want to put a dx or dy or dz or du or dw or dt, whatever the variable needs to be. In this case, since it's f of x, it's dx. If it was f of y, it would be dy, but we need to have that as the closing parenthesis there. It's a remnant of that delta x, but it also tells us the variable that our integral is being evaluated with respect to. And so we want to make sure that we have that present. Otherwise, we're going to be in trouble. Now, the f of x part itself is called the integrand. That's the name of that, the function integrand. And for the integrand, we're putting it in terms of the letter f of x right now. But if f of x was the sine function, then we would write this as our definite integral from a to b of sine of x dx. Or if it was, for integrand, if our function was x squared, then our integrand would be x squared. Right now I'm just using the name f of x, but that's sufficient there. So you got to get used to this notation. This notation means that we're, everything that we're doing up here at the top, taking a limit as n goes to infinity of this sum from I equals 1 to n, f of x sub I star times delta x. That they mean the same thing. They represent area bounded by a curve. Okay. Wow, did I say that out loud? I did. Okay. Yeah, but that's what we've been talking about. Area bounded by a curve. So when you see right now in this section, until we develop the idea further, when you see this definite integral, you need to think that is the area bounded by f from a to b, bounded by f and the horizontal axis from a to b. And so there are other possible ways of calculating this. As of right now, we know how to approximate this integral using rectangles and maybe trapezoids, if you remember that from pre-calculus or from a previous class. And if you don't, you need to get some review on that. But that's okay. To evaluate this exactly, either we have to know a formula for the shape of the curve. Maybe it's a semicircle, or maybe it's just a bunch of straight line segments that we can then find the area of using basic geometry. Or we need another technique, and we're going to learn other techniques later on in this chapter that'll allow us to evaluate this for some certain functions exactly. This is just an introduction to the set of symbols that you can become comfortable with this. Okay. Very, very quick example here. If I was to ask you to evaluate, just something really simple like we're going to take our integrand to be 2x plus 1. We're going to integrate with respect to x. And let's say we did this from 0 to 3. All this is an area. If I were to calculate or draw rather the graph of 2x plus 1, I can do a slightly better version of that. 2x plus 1 would hit right here, and then we go up 2 over 1, up 2 over 1, up 2 over 1. I need to get out to 3, so that's why I did it that many times. And you can hear me sliding around a little bit. But if I were to draw a reasonably straight line in between there, then all I'm doing is, to evaluate this definite integral, is calculating this area right here. And that area is just a trapezoid. And so if I remember how to find the area of a trapezoid, I'm good to go. Or if I don't, I can break it down into some smaller regions, a rectangle and a triangle. And then I can just add those areas together. The rectangle is 3 times 1 for that area. The triangle has a base of 3 and a height of 1, 2, 3, 4, 5, 6. And then, of course, we have to divide by 2 because that's the formula for the area of a triangle. And make sure I'm not making any mistakes. Yeah, so the value of this definite integral is 12 because we just calculated the area bounded by the curve. One more quick thing before we move off or allow you to go do a Desmos activity or something like that. Let's say I did want the definite integral from, say, pi over 3 to, let's go, we'll just keep it simple. Let's go to pi over 2 of the sine function, so sine of x dx. Since we haven't learned very much yet about this process of finding a definite integral, the way we would do this is just by one of our approximate methods, one of our Riemann sums. So very quick sketch. So the sine graph starts at 0, goes up to 1, just something like this. This is where pi over 2 is, right over here. No, that's pi. I'm sorry. Pi over 2 is 1 right here. I'm going so fast, I'm making mistakes. But pi over 3 is a little bit smaller. I am definitely not in the right location here, but if we were trying to find the value of this definite integral right now with the skills that we have, the best we could do is to do one of our Riemann sums, one of our approximate methods. I want the area bounded by this curve or an approximation to it. So depending on the problem, it might tell me to use 3, 4, or more rectangles or trapezoids. I can use left, rights, midpoints, or anything else, depending on, again, how the problem was asked. So until we learn a little more skill about how we might evaluate this precisely, we would do one of our Riemann sums to approximate this using, so I'll just put this, approximating using rectangles or trapezoids, if you remember how to do that. So for now, this brief introduction, okay, the area was given to you as a limit. Now we have this new set of symbols, this definite integral. The a and the b are the endpoints of our interval on which we're evaluating this or calculating this area. The function f bounds it above. The x-axis, for example here, bounds it below. And start getting used to this notation because we're going to make it more and more, or make more use of it as we move forward. Go study.